So now we can proceed to define annihilation operators. We have this relation that we worked with for the creation operator. And from this, we can see that if we pre-multiplied on the left with this bra vector with one particle in state k, then what we would have multiplying on the right with the same bra vector would give this relation here. This inner product of a state with itself, since by choice these states are all normalized, just gives us 1. So the result of this element here is this number. Now, we can take the complex conjugate of both sides, but since these are numbers, of course, the complex conjugate and the Hermitian adjoint are the same thing. A complex number is just a 1-by-1 matrix. So formally, taking the Hermitian adjoint of both sides, we are going to start with the left-hand side here. Remember that the Hermitian adjoint of the product of two terms is the flipped round product of the Hermitian adjoints. So we can take this here, the creation operator operating on this state with 0 in state k, as one of the elements. So here's the Hermitian adjoint of that, written out formally. And the other element was this one, this bra vector. So here's the Hermitian adjoint of that, written out formally. We can use the same rule again on this product. So we get the product of these two flipped round and Hermitian adjointed for each one. So here's the Hermitian adjoint of this term. Here's the Hermitian adjoint of that term. And remember that the Hermitian adjoint of a Hermitian adjoint takes us back to where we would have started. So formally then, just by using that rule, we can rewrite the left-hand side here in this form. The right-hand side was just a real number, and so the Hermitian adjoint, or complex conjugate of that, is just the same real number. So we can deduce here that the effect of this operator on this state is to turn it into the state with 0 particles in state k and multiply by this -1 to the power sk, because that will give us this relation. And we can, if you like, choose this operator to have this property, and that's what we do. So we choose this operator, we'll call it the annihilation operator formally, to have this property. Hence, where this operator creates a fermion in single particle state k, provided the state was empty, we see from this relation we have just deduced or defined that this operator annihilates a fermion in single particle state k, provided that state was full. And therefore it's called the fermion annihilation operator for state k. The annihilation operator acting on the Slater determinant progressively swaps the row corresponding to state k in the determinant with the one below it, until that row gets to the bottom of the determinant, in which case we remove it. And of course we have to simultaneously remove the rightmost column of the determinant, the last column. And that's in an exact inverse fashion to the process we used with the creation operator. Using the relation that's analogous to the one we had for the creation operator, in which this operator, the annihilation operator, operating on a state with no particles in the single particle state k, would give us a 0-length vector in the Hilbert space. So this is stating that if the single particle state was to be empty to start with, we cannot annihilate another particle from that state. So this is a property we give to this operator, if you like. We can argue similarly that we'll end up with this kind of anti-commutation relation. The arguments would exactly parallel the ones that we went through for considering the creation operator and its anti-commutation relation. And just as for the creation operator, this will be our annihilation operator anti-commutation relation, and it will be valid for all choices of states k and j, similarly to what we had deduced for the case of the creation operator.